Singing has a cool starter on both concepts.
Yeah, we are like around, I think, almost done. My teachers went through all the formulas and everything.
Huh? So fast,
Yeah,
Can you
but
understand everything?
no, I can't understand. Because I don't know, my teacher's going through a lot.
Yes, yes. There are at least 8 formulas. Okay, so anyway, I'll go through them. Okay, as always, I'll record this session. Come, Rachel, ready to copy down?
No.
All of the above.
Following here. Okay, come, let's start. Go through the formulas. There are about 8 of them. Okay, number 1. Come, Rachel, what did I put here? One, let me turn this on. Okay, you'll be using this formula for the longest time. And this is the basic one. Come singing, MR stands for singing.
The mass of the element. Like, I don't know, I don't know how to say it, sorry.
All right, it stands for relative molecular mass of a substance. Can be anything, can be element, can be compound. Can I assume your guys have no problem with calculating MR? Rachel, okay with it? Okay, so I can go through. Now, the only thing you got to be careful is, now obviously the mass must be the same substance. So you must know what substance you're interested in, and obviously the mole you apply the same substance to. Okay, this is the part that some students should get wrong. They mix up the substances in the same formula. Hi, Dylan. All right, so just looking at the focus this. Dylan, we are going through the mole concept. You got any questions? How is the WA? Okay, have you taken back the marks? Not yet. Hmm. Okay, so that is the basic one. Number two. Okay, teacher, has your teacher gone through concentration? Oh, okay. The other one is number of particles. This one can be quite difficult to use as well, but you still have to know the formula. Number of particles is based on number of moles K times Avogadro's number if multiplied by a factor. Okay, so this is your Avogadro's number. Now, for info, this number is given in your periodic table, so you can refer to that and no need to remember. Now, the tricky part is this particles refer to what? This is the difficult part. You've got to look at the question carefully. Is it atoms? Molecules? Sometimes ions? These are the common ones. Now, the factor is tricky as well. It depends on the question. I'll give you a couple of examples. Hey, Dylan, yeah, no problem with all this. No. Okay. No. Oh, okay. So then we can ask you. Right. So let's say I have 1 mole of CO2. And then they ask you number of molecules. So basically you get 1 mole times Avogadro's number times what's the factor? Come, Dylan, CO2 exists as what? Or what's the structure for CO2? It exists as what's the structure? Remember the structure you had giant ionic structure, giant covalent. Yeah, simple covalent. So in other words, this exists as simple molecules. And they are asking you for molecules, so therefore my factor is 1. But what if the question asks you for a number of atoms? Now, my CO2 is still 1 mole, so I keep 1 here. Avogadro's number is a constant, no change. Now, in this case, then what's my factor, Dylan? Yes, because this guy has 3 atoms, 1 carbon, 2 oxygen. So, yep, factor is 3 now. Okay, one more example before we move on. Let's say I have 5 mole of sodium sulfate. Okay, so they ask you number of cations. Now I use the same formula. Mole sodium sulfate is 5. Avogadro's is still the same constant, same number. But what is my factor here? Ethan. Now the thing is this, look at this guy again. 1 unit of this guy has how many cations? Richard? Okay, good. So it's 2 cations. So therefore my factor is 2. On the other hand, they can change the question and ask you, what's the number of ions? Well, I still have 5 moles. I still have Avogadro's number. Dylan, what's my factor now? Number of ions. How many ions are there in 1 unit? 5. Okay, let's break this guy down. Okay, if you dissolve this in water, you will get 2 sodium plus, yes, 3 ions, and 1 SO4 2 minus. So altogether there are 3 ions, and therefore my factor is 3. Okay, Richard. All right, 2 sodium, 1 sulfate, total 3 ions in 1 unit. So therefore, my factor is 3. So anyway, the point is you've got to check your question. What are they asking for? All right, just now I asked for cations, but now I'm asking for ions, and that will decide the factor that you are using. Okay, questions, anyone? Yeah, singing, you can ask too if you have questions. Oh, okay, then I shall move on. Richard, all right. Almost, it depends on the on the substance. So since you asked about atoms, let's go further a bit. Suddenly the question asks you number of atoms. It's still 5 more, right? Yes. So how many atoms are there? Yes. 4, 5, 6, 7. 7 carefully. 1, 2, 3 plus 4, 7. Can? So that's why it's 7 now. Because they asked for atoms. Okay, so this guy has 7 atoms. That's why the factor is 7. So it depends on what the question asks for. That will decide the factor.
How many hours? 24.
Dylan, so what's your teacher teaching now?
In the latest topic was
QA.
human to environment.
Okay, that's supposed to be the last chapter. That's it. And so I shall move on. Yes, Ethan, also environment. Oh, that's the last chapter already. You look at your textbook. And Ethan done? Done writing? No. Anyway, as I said, this session is recorded, so I'll put out the link in the Telegram group chat. Okay, let me just add a little more stuff. Number 3. No, number 3, important. This equation is only for gases. Therefore, check your question. You know what they like to trick you with? So let's say they have this simple give you, okay, maybe not C. Let's use something else. H2. Now, I think it goes without saying the first 2 reactants or the 2 reactants are typically gases. But this one is the tricky part. Now, you've got to look at your question. They tell you the reaction is carried out at room temperature and pressure. Dylan, what's room temperature? Is there a value? No, it's not the room you're in now. It's for under chemistry, it's a fixed value, it's 25 degrees Celsius. And therefore, you can safely deduce that this guy is a liquid. And therefore, you cannot use the formula. Or let me be specific, you cannot use the gas formula. Whole concept. Now, on the other hand, if they tell you the reaction is carried out at engine temperature, or in car engine, right? In a car engine. Now, of course, you expect it to be very hot, and therefore you would expect this to be a gas. And that is when you can use the gas formula. So just be very careful. They like to test or trick you with water. Okay, back to the formula. Basically, volume for gas. And our fixed units for this volume is in dm cube. Don't mess up the units. Equals to mole of the same gas times 24 dm cube. Yeah, simple formula. But like I say, be careful on dm cube. Oh, before I forget, there's an assumption. The assumption is this formula only works at room temperature and pressure. Now, let's just make sure you guys know what is BMQ. Michelle, how many cm cube is 1 em cube? Okay, remember after today. Also, they can give you the units in cm cube. Make sure you know how to convert. Make sure. Now, occasionally, the question may even give you volume in meter cube. Occasionally. Now, this is 1000 dm cube, which means 1 meter cube is 1 million cm cube. Yeah, that's all. It's not like physics where you have all the other funny units. You only have dm cube, cm cube, and meter cube. That is all. Okay, can find you the conversion. Right, so very simple. Let's say I have the example. I have 100 dm cube of CO2. How many moles of CO2 is this? Yeah, Dylan.
Good. Over 24.
Yep. 100 over 24 is 4 point something. Oh boy.
4.16. 4.17.
Oh, okay, good enough. Okay, so yeah. Ethan, can I? All right, so there's the gas formula. So of course, anyone has questions, please voice out. Otherwise, I shall move on. Ethan, are you in the same class as you? Okay. Right, so I shall move on. Next formula, or next 3 formulas. Okay, next 3 formulas, look up only for aqueous solution. Check your system, is it an aqueous solution? Now, before I go further, what aqueous solutions do you know? Richard, give me one. What kind of, where do you encounter aqueous solutions? First one, acid. Yeah. Anytime the question said use the word acid, automatically it's aqueous, or they use the word alkaline, automatically it's aqueous. Salt solution? Salt solutions? Provided the salt is soluble. Hopefully you still remember your solubility rules. These 3 are the common ones that you see in your questions. Occasionally, you see the 4th one. These are quite unusual, but they can come organic substances in water. And I'll give you a couple of examples, the more common ones at least. Sugar, ethanol. This can be dissolved in water, so they can become aqueous too. So check, does your question, do you encounter them in your question? So back to the formula itself, number 4, right? I think, yeah, number 4. This one confirm coming up. Concentration of solids. I stress on the word solute. That means you better know what is your solute. And the units are very specific. Mole per dm cube. Okay, equals to mole of solute divided by volume of solution. Now, as I said, mole is a unit by itself. Volume? What kind of units do you want? Did you notice on the left-hand side, its concentration is per dm cube. Therefore, my solution volume must be also in dm cube. Again, don't mess this up. Lots of students have messed up the dm cube. Lots. So yeah, that'll be one of them. But what is concentration anyway? So let's say I tell you, you have this beaker of acid, let's say HCl, right? And they'll tell you 2 mole per dm cube. So that means I can just pipette out any volume. Let's say I pipette out 1 cm cube. It's just a very tiny amount. Okay, guess what? The concentration is still the same. It's still 2 mole per dm cube. Okay, on the other hand, I pipette out 100 cm cube. Okay, this is a much bigger volume. Guess what? My concentration is still the same. Yes, Ethan, question. Okay, concentration is still the same. I don't care how much you take out. But what is different? Let's look at this case. What's the number of moles of HCl here? What's the number of moles of HCl here? Did you look carefully at the formula? This one here. I can rearrange this formula now. I can rearrange it until it becomes, this is my favorite version. Moles equals to concentration times volume. It's up to you which version you want to remember. So if I hope you can see this formula can be rearranged into this version. Okay. So I use the formula here, this one, and I use it here. What's the concentration? 2. Maybe I write the formula in as well. I put it as CV. Concentration is 2. Check your units, make sure it's in mole per dm cube. What's the volume? Dylan?
0.001 kg.
Good. In case you didn't notice, 1 cm cube is 0.001 dm cube. And of course, this value gets substituted here. So if I work this out, how many moles do I have? HCl 0.002. Now, for the second example, same case, I used exactly the same volume, same formula, concentrations and volume. Concentration is still the same, it's still 2. Check units, mole per dm cube. This one, eaten. What's the volume? What volume should I? 0.01. I use 100 cm cube. 100 cm cube. 100 cm cube is how many dm cube? Yes, 0.1. Okay, so I multiply by 0.1 and my answer is 0.2. Now, as usual, don't be careless. Right, so yeah, that is for concentration. Oh, by the way, we haven't touched on any reaction yet. We are just touching on the formulas. Okay, let's look at formula 5. This one may or may not come up. It's still a concentration formula, concentration of solute. But look at the units. Now it's gram per dm cube. So therefore, the formula is mass of solute. Check your units. In grams. Over volume of solution in dm cube. Again, I hope you notice left-hand side gram. Therefore, numerator is gram. Left-hand side denominator is dm cube. So right-hand side denominator is dm cube. Okay, there's a certain consistency to it. Okay, for this case, they may tell you a story. So let's say I have this beaker again. Okay, this case is NaCl. And they tell you concentration of this salts in the water is, let's say, 10 grams per dm cube. Now, guys, be very observant. Once you see this, they may not tell you, once you see this units, gram per dm cube, automatically you should know that this is a concentration. They won't tell you it's concentration, they just tell it's 10 grams per dm cube. Once you see that, you should know it's concentration. Oh, yeah. Yeah. Very late. Oh, okay, long never. So what happened is if I take out here she is 10 cm cube. Hi Sabrina. Okay, I take it out and put it into a big fat test tube. Then the question asks you, mass of NaCl inside that test tube. Okay. Okay, can't work it out. Should be quite easy. All right. I pipette out 10 cm cube in the test tube. They want you to find the mass of sodium chloride in the test tube. What formula should you use? Ethan, can? Dylan, what's the answer?
0.1.
Okay, good. Now, same thing. I can rearrange this formula as equals to concentration times volume. So I apply this formula here. And for sodium chloride, concentration is 10. Volume 0.01. Again, make sure you notice 10 cm cube convert to dm cube is 0.01. Yeah, substitute this here, and that's it. I get the answer. Don't forget your units. Okay, last one. Last formula for concentration. I mean for aqueous solution. Look at this two, number 4 and number 5. Number 4 is concentration in mole per dm cube. Number 5 is concentration in gram per dm cube. And I relate them in the same formula. Okay, for the last formula, depends on you. You may or may not want to use it. Okay, very simple. Concentration of solute in mole per dm cube equals to concentration, of course, of the same solute. Gram per dm cube A divided by m of the solute, of course. Reminder, for every formula, every single formula, they have to be pertaining to the same substance. Solute, same solute, same solute. Do not mix up different substances in the same formula. Okay, very, very simple example again. So let's say I use the same beaker here, sodium fluoride. Huh? Can you find the concentration of sodium fluoride in mole per dm cube? You already know this, right? Concentration in gram per dm cube. Can you find the concentration in mole per dm cube? Just take 10 divided by the mR. Ethan, look up what's the mR of sodium chloride. You need periodic table. Okay, basically sodium is 23. Chlorine is 35.5. Okay, so it's 10 over 58.5. Just look up the number. Dylan, what's the answer?
0.17.
17? Okay. How many formulas? 6. Okay, 2 more to go. Sabrina, your class is doing this as well, right? How can you follow? Oh, okay.
Other than that,
Mm, okay, don't worry. You're not the only one. But one question, most is a SI unit. Why do we even want to have this SI unit there? Why can't we just use mass, so many grams, react with so many grams, and that's it, end of the story? Why do we want moles anyway? Or why do you even bother to calculate moles? Okay, I shall wait for Sabrina to finish. But anyway, you may want to jot down somewhere. The simple reason is for reaction. Whenever there's a reaction, think about moles. Later you see why. But for now, remember that when there is a reaction, think about moles. Okay, so let's step backwards and go back to Formula 1. Now, let's have a simple equation. Okay, simple one. This one I had given you earlier. Okay, can't balance it, fill in the state symbols. Now, in this case, for water, I assume it's done in the car engine, so it will be in the form of steam. So put it as gas. Normally, the question will mention something like that. Maybe they tell you it's in the car engine. Or in the engine. Not in, I don't think you'll find this in the car, but more like in the engine. Let's just say in the engine. It's going to be really hot, so therefore you expect it to be in the form of steam. Okay, come. The amazing thing about mole is this. There's two ways to interpret this. I can interpret it as two molecules of H2 react with one molecule. Make sure you can understand this part. One molecule of O2 to give me how many molecules of water? 2. There's one way to interpret it. Now, the second way to interpret this is 2 mole of H2 react with 1 mole. Remember, this is a reaction, so I can use mole to give me 2 mole of water. So everything is in moles. 2, 1, 2. Can you use mass? Yeah, you can, but it's going to be really troublesome. Huh? I just pass you the periodic table. Sabrina. Dylan, Ethan. I can rewrite this another way. I mean, okay, let's look at the third interpretation. But this one is very unwieldy. 2 moles of H2. What's the mass? How much does it what's the mass of 2 moles H2? Yes, 2 grams. Look at this formula. Mass equals to mole times mR. Okay, mR for H2 is 2. I hope you all can see that. So it's 2 grams, no? 2 grams of H2 react with 1 mole of O2. What's the mass? 1 mole of O2? 16? What's the mR of O2? Sabrina? Yes, 32. Okay, just be careful. It's O2. So the mR needs you to take 2 multiplied by 16. 16 is the AR, which is found in the periodic table. So it's 32 grams. Then Dylan, just be careful. So basically 2 grams of H2 react with 32 grams of O2. You give me 2 moles of water. What's the mass for 2 moles of water? 36. Is it 36? Did I miss out something? No, I did miss out something. I miss out something. Okay, come. I miss out something. Yeah, you're right. This is 36. But I miss out something in front. One.
4 grams of H2.
Yes, good. Be careful. I mentioned 2 more H2, right? So if I look out the formula, mass equals to mole times mR. The mole is 2. mR of H2 is also 2. So that's the thing I miss out. So it's 4 grams. Okay, so there's not 2 grams, it's 4 grams. Ethan can follow. And hopefully you notice by now, look at the left-hand side. Add the masses together, 36 grams. Right-hand side, 36 grams. So this is your conservation of mass. See that nothing is lost, obviously. But look at the mass, so unwieldy. 4 grams plus 32 grams gives you 36 grams. It's so difficult to express this, So therefore, that's why they use number of moles to express, because the number of moles is exactly the coefficients in the equation. That's why it's a lot more convenient to use moles. Okay, that's the short answer why you're using moles. But let's go a bit even more than that. You use the same equation again. Try to follow this one. This one is quite difficult, but it's definitely coming up. Okay, so I use the same reaction. Balance, check is balance. Check your state symbols. So therefore, the theoretical ratio is 2 is to 1 is to 2. Okay, but obviously in real life, you're not going to have such nice numbers. So what if I give you this actual amount instead? Actual mole. Let's say in an experiment, you're given 10. All right, you're given 10 moles of H2, and you're given 5 moles of O2. How much water do you get in terms of moles? Yeah, Sabrina. I hope everybody can see. I have 10 moles of H2 react with 5 moles of O2. I should get 10 moles of water. Perfect, right? Okay. Richard can follow this one. But your question is not going to be so high. It's going to give you 10 moles of H2 and 2 moles of O2. Now we have a slight problem, right? How many moles of water would I get? Come. Okay, let's go through this. I'm not going to ask you. I'll go through this. Now, the problem is one of them is limiting. Now, the word limiting only applies to reactant. So I don't have to look at the right-hand side. I only look at the left-hand side. So let's say assume if H2 is limiting. Okay, maybe you want to spare some space somewhere to write down some guidelines, huh? Some general guidelines. Okay, number one. Whoever is limiting is completely useful. Or completely reacted. Okay, therefore, no remainder, nothing remains of that reactant. Okay, so that's the first guideline. Keep this in mind. Now, go back to the go back here. So if H2 is limiting, that means I have 10 moles of H2. I will use up all 10 moles. Okay, I would use up all 10 moles. How much O2 do I need theoretically? Look at my ratio. Look at my theoretical ratio. 2 is to 1. 10, 2 is to 1. So therefore, 10 is to 5. Okay, so based on theory, 2 is to 1. So if I have 10, then it's 10 is to 5. But look at my actual amount. I only have 2 moles. Do I have 5 moles? No, I don't. I only have 2 moles. So therefore, what's the conclusion? We only have 2 moles of O2, no? So the conclusion is this. O2 is limiting. And the second guideline, you can add in number 2. If there are only 2 reactants, most of the time, but sometimes your question may give you more than 2, then it becomes very troublesome. If there are only 2 reactants and 1 is limiting, the other is in excess. Take note of this word in excess, you're going to see it very often. In excess. So therefore, who is limiting just now? O2, right? And therefore, I can safely conclude H2 is in excess. Oh, by the way, my guideline is vice versa. That means if let's say I know one reactant is in excess, the other is limiting as well. So take note, because your question may not tell you who is limiting, they will tell you who is in excess. Okay, so maybe in the reverse is true. If you know who is in excess, the other one must be limiting. But back to my this step here. Notice what did I assume earlier? I assumed that H2 is limiting, right? But in the end, I found out that O2 is the limiting one. So therefore, this assumption is wrong. Because I at first assumed H2 is limiting, but in the end, I found out it's not true. Okay, can. Oh, you can remember this. Anytime you see a reaction, always determine who is limiting. Okay, think about that. Think about that. Serious. If not, it's going to screw up everything, all your calculations later. Find out who is limiting. Okay, I'll tell you the reason very soon, but just keep that in mind. Anytime your question involves a reaction and involves calculations, determine who is limiting. Sometimes the question is kind enough to tell you, then okay, fine. But if not, you have to work it out. But let's go back here again. Ethan? Okay, now. I mean, make sure you really are okay. Okay, let me just wait for the viewers. Now, what if at the beginning, I'm so smart, I make a correct assumption. Go back here. Theoretical ratio is still 2. 2 is to 1. Actual mole ratio is 10 is to 2. What if I decide to assume this? If O2 is limiting. Yeah, I make this assumption. O2 is limiting. Now remember, O2 is limiting means all the amounts will be fully used up. So 2 moles will be fully used up. How much H2 do I need here? Okay, try to follow. Just now, by theory, is 1 is to 2. So 2 is to, yes, good. 2 is 4. Now look at my actual amount. Do I have 4? No, I have more than 4. Okay, so you have more than 4 moles, and that already tells you you have more than enough, and therefore OH2 is in excess. And since H2 is in excess, the other guy, O2, must be limiting. And therefore, my original assumption is correct. Okay, so far I've only identified who is limiting and who is in excess, but I haven't done any actual calculations yet. But before we move further, I'll give you one more example. Just to make sure everyone is on the same page. Okay, come, let's give you another one. Okay, maybe not. I want to make sure you get your basics correct first. Now, let's have a new reaction. So, simple one. Very simple. Okay, come everyone, work out the whole reaction, fill in the products, balance it, add in the state symbols. Okay, obviously you should recognize this is an acid alkaline reaction. Okay, once you're done, make sure you check against my answer. You should get it right by this time. Okay, of course, if you have problems to voice out, make sure you realize that the products are salt and water. Make sure you know how to balance it. Okay, so come, same thing. I write my theoretical ratio. Very simple. Look at the coefficients. 1, 2, 1, 2. Okay, so these are based on the coefficients of your equation. But your question gives you some funny amounts. Obviously, it's not going to be just nice numbers like 1, 2, 1, 2. It's going to give you 50 moles of H2SO4. All right, 70 moles of sodium hydroxide. Yeah, I think it gives you any amount to mix them together. Okay, come find out who is limiting and who is in excess. Ethan, which reactant is limiting? Okay. Richelle, which reactant is limiting? Oh, wait, okay, sure. Come, Ethan, and maybe the rest as well. So we follow your assumption, or we follow your answer. Now, Ethan, let's follow your assumption. If H2SO4 is limiting, if no, it's okay, learn from all this. Then I would have used up the entire amount. Okay? Okay, we follow this assumption. H2SO4 is limiting, so I use up all the H2SO4, 50. But based on your theoretical ratio, 1 H2SO4 translates to 2 NaOH. So 50 translates to, yes, good, 100. Do I have 100? No, I have less than that. So therefore, NaOH is less. Anything less means limiting. So therefore, NaOH is limiting. So that's the first thing you deduce. The second thing is obviously H2SO4 is in essence. And the third thing, this assumption is true. But that's fine. At least you identify who is limiting. Okay, Ethan? Yeah. Reach out, okay? Ethan, can
This is that's the whole formula is like 200.
anything to ask? No, can this one must be can no. Singing, I assume you have nothing to ask. If you do, voice out. Angel too, if you have something, voice out as well. Now, it comes to the the third point. Why am I so concerned about limiting reactant? Because of this, add in the third guideline. Oh, no space, Sabrina. The limiting reactant determines something important. It determines the amount of products formed. This is super important. This is why I'm so concerned about finding out who is limiting. So at the end of the day, why do you even want to run a reaction? Why do you want to perform a reaction? Most of the time is to get the product. Okay. So let's go back to our Done, Richard. Now let's go back to this one here. This reaction just now we haven't finished with it. Now I have determined who is limiting. O2 is limiting. So highlight O2, O2 is limiting. What's my product? Only one, water. How many moles of water do I get? What's my value here? Now, what I do is, theoretically, one O2 gives you 2 water. So therefore, 2 O2 gives you, you know, how much water do I get? One O2 gives me 2 water, 2 O2 gives me 4 moles of water. So this is the amount of product I got. It's based on 2 moles of O2. Okay, not based on 10 moles of H2 because H2 is in essence, so I don't care about H2. I'm only concerned about O2. So I get 4 moles of water. This is the product I want. Anyway, there's only one product here. Let's go to the other one. This one. This one is a bit more, I won't say very complicated, just slightly more complicated. How many moles of products do I get? Now, who is limiting again? Limiting? NaOH, right? So let me highlight that. So I have how much? 70 moles of NaOH. Okay, be careful. Highlight the actual amount. Don't get highlight the some assume amount. Highlight the actual amount. NaOH is limiting, right? So highlight this. I've actually 70 moles of NaOH. So how much sodium sulfate do I get? How much water do I get? Yeah, Sabrina? Sodium sulfate? Yes, 70. How do I know? Because I look at my theoretical ratio. 2 is to 1. So 70 is to 35. And likewise for water, 2 is to 2. 2 is 2, so 70 is to 70. Okay, so these are the amounts of product I got. Notice I don't care about this guy, because this guy is in excess, so I cannot use this number to calculate these 2 numbers. I use the limiting reactant number to calculate these 2 big numbers. But guess what? Did you notice this fraction is what? Equals. So they're not going to give you these nice numbers. No? They're going to give you concentration and volumes. Now, let's use the same equation or same reaction. Before I go further, any question? Okay, notice we still have 2 more formulas to go, which I'm not going through today. Those 2 are really difficult. Sabrina, has your teacher gone through empirical formula? Yeah. Yes, sir. Okay, that one is good. I'll do it next week then. Dylan, can still remember empirical formula?
I think
You think so? Okay. Come guys, same reaction. But guess what? Your question is going to give you this H2SO4. They give you 100 cm cube. EM cube, not DM cube. And concentration is 0.2 mole per DM cube. Then they'll give you 50 cm cube of sodium hydroxide and concentration 0.5 mole per dm cube. Reminder, aqueous, therefore they can have concentration. Come, work out who is limiting. What should you do first? Well, of course, you can always write the theoretical ratio if you want to. So as always, I write out the theory. 1:2, giving you 1:2. Use your concentration formula, of course. Formula number 4. Because the concentration is in mole per dm cube, so you have no choice. You have to use formula number 4. Anyway, I'll write it down in case you are stuck. Yeah, I'm using formula number 4 in case you want to. And I apply formula number 4 to each reactants. Okay, same formula but different substance. Okay, then I fill in the actual values. Okay, same thing, I make an assumption. Of course, if you're really experienced, you can immediately know who is limiting already, but it's not just make an assumption. Okay, so the limiting reactant will be fully used up. So ratio 1:2, so 0.02 is to 0.04. Now, do I have 0.04 of sodium hydroxide? No, I don't. So, okay, you only have less than that. Okay, in actual fact, you only have 0.025. So whichever is in less amount, that is the limiting. And therefore, the other guy must be assessed. Okay, and therefore, further down the road, you know that this is wrong. But it doesn't matter, you have already determined who is limiting. Anyone has questions about this? Did everybody manage to find out limiting is NaOH? Can. Okay, so lastly, I want you to fill in the numbers for the products. Use the actual amount, of course, actual amount of NaOH. So NaOH is limiting. Use that number and find out how much sodium sulfate you have, how much water you have. You know water, I'm not so concerned because water is everywhere in the system. Come, Ethan, how much sodium sulfate will I get? Okay, good. Good. Water, Ethan? Yes. Any questions from the rest? Yeah. Richard? Still writing. Okay, let's have enough time for one last example. Again, nothing new. I use the same reaction again. Let's look at this guy. Let's look at the same reaction. This one. Okay, nothing new. Okay, come. What if I tell you this? Same thing, theoretical ratio, nothing new. You just rewrite all the numbers there, 2 is to 1 is to 2. But look at the actual amounts. I give you the actual amounts in DMQ. I give you 200 DMQ of H2. And I give you 150 EMQ of O2. It's not in moles, it's not in concentration units. Check, make sure all are gases. Find out who is limiting, who is in excess, how much product is formed. 3 questions only. Oh, guys, can you add in one more guideline? Just now I had number 3, right? Can you add number 4 as well? Oh, no space after Rina. Oh, this guideline is important, very important. Make sure you remember the last one. If T is reactants are gases, the mole ratio equals to the volume ratio. Provided both reactants are gases. Okay, so in this case, it satisfied that condition. If a problem, you can follow what I'm writing. Just use the same thing, same procedure. If H2 is limiting, okay, so all the H2 will be used up. So how much O2 do I need? I need 100. Okay, why has 100? O2? Yeah, I have more than that. Okay, actual O2 is more than 100, so therefore O2 is in a sense more than. And therefore H2 is indeed limiting. And therefore my assumption is correct.
Yes.
Sabrina, how much water do I get in volume? Yeah, good. Okay, so I'll circle out the limiting vector H2, and therefore it will determine my product. 2 is the 2. So 200 will give me 200. Yeah, cheap of course. Check, make sure it's a gas, otherwise you can't do this. So I get 200 dm³ of steam as my product. Dylan, okay.
Yeah.
Then you may have to go back and digest a bit. Oh, is it? You got the whole question wrong. Oh, is it? No, it's okay. Learn from that. All right, guys. Any final questions? Singing, Angel, any question? Singing, Angel, no question. Any question?
No.
Okay, great. All right. So if not, then somebody write something. Oh, Angel, no question too. Okay, if not, then I shall end the lesson here. So that's all for today. See you next week. Okay.